Welcome to part 2 of our soil water chapter, where we're going to be discussing movement and availability concepts. Basically, we're talking about water flow in soil. Infiltration, as you remember, is a surface phenomenon. It's basically the rate at which water comes into soil at the surface. So we're going to start talking about what controls infiltration. Things like soil texture, structure, organic matter, preferential flow, the amount of water already in the soil, compaction, and crusting problems. Texture affects infiltration because it basically controls the size of micro and macro pores, which will, of course, affect how water moves into and through soil. Structure also affects micro and macro pores, as does organic matter, because organic matter helps to influence soil structure and how strong the units are. And the stronger the units, the better pore space and the easier flow. Preferential flow, amount of water already in soil, both of these things have to do with either the presence of biospores or if the soil is already saturated, then, obviously no more water can come in, and so that's going to decrease infiltration. We're going to start talking about water flow through stratified soils. Remember, soils have horizons which can vary in texture and structure. So, as we go through a soil profile, generally soils will gradually shift from one horizon to another, but sometimes we end up with super different horizons stacked on top of each other. So, for example, we could have a drastic change in texture, or maybe one of the horizons was drastically compacted. These things will greatly affect how water moves from one horizon to another. So in this experiment example, we had a silt loam that was placed over sand. So remember, silt loams are finer in texture, and so they're going to create way smaller pores, which means we have really, really thin, tiny pores on top of giant macropores. So what happens is water comes into the surface layer, and because of the difference in texture, we're going to ask the following question. If the water stops moving downwards after reaching the sandy layer, at what point do each of the following potentials dominate water movement? Let's talk about that a little bit. So ultimately, when water comes into that silt loam horizon, it's going to be governed by matrix potential because it's going to be unsaturated. The tiny pores in the silt loam layer at the surface have a lot more ability to hold on to water and to suck it through. And so they basically hold water tighter until it reaches saturation. Once that layer gets fully saturated, then gravimetric potential takes over and the water flows into the subsurface with the larger macropores. Ultimately, what this was before it flew into the subsurface is called a perched water table. So this stratified soil texture situation ultimately can end up in a perched water table. The same thing can happen when we have sand over larger fragments like gravel. Again, we can get a perched water table. Vertical mulching is one tool used to help get water into soils at greater depth when we have stratified layers where a perched water table may occur. So as we talk about moving water through soils and we're discussing the various soil water potentials, I just wanted to remind you that gravitational water occurs at saturation, matrix potential occurs at unsaturated points. So what we call these various points is at negative 33 kilopascals when we have roughly 50% available water in the pores, we call this field capacity. At Negative 1500 kilopascals, we're starting to get to the wilting point of plants. We only have about 25% water. And so I want you to remember that the plant available water is held between negative 33 and negative 1500 kilopascals. So the total plant available water is field capacity minus permanent wilting point. And unavailable water is held at soil water potentials that are at negative 1500 kilopascals going all the way to negative 800,000 kilopascals, basically up and dry. So there's definitely a relationship between soil texture and available water. We find that the smaller the texture, the more available water over time, because it has more of those micropores that can hold on to water for longer periods of time. And so water moves way slower through these textures. And so it just sticks around longer and makes it easier for long-term plant use versus the more coarse textures like sand and sandy loam. They're going to have much more macropores, which is going to move water a lot faster. Ideally, the perfect amount of available water lies in the loam and silt loam range because water moves at a rate that's ideal for plants but still provides long enough for the roots to get saturated. So we're going to start tying all this into the hydrologic cycle and our water use. So first, of the water available on the Earth's surface, we have 97.2% of it locked up in oceans and seas. 2.8% is fresh water. Of that 2.8%, we have about 2.16% locked up in ice and 0.62% in groundwater, and only about 0.015% locked up in lakes and then in soil pores. Soil moisture accounts for about 0.005% of that, and lakes account for about 0.009%. The other 0.001% is in the atmosphere, rivers, and within cellular bodies, in biota. So as we talk about the water cycle, essentially we have bladders in the sky, aka clouds, that as they fill up, release water to the surface where it either congregates in surface streams and rivers, pools and lakes, or runs down to the ocean, where it's then evaporated back up into the atmosphere to continue the cycle, or in some cases, water goes into the ground and becomes groundwater, which can also flow towards the ocean, but we also see salt intrusion on some of those marine coast areas. We also have a significant amount of water locked up in ice that melts during certain times of the year to be put back down in the cycle. So what's included in the hydrologic cycle is watersheds, evaporation and transpiration, interception at various points, infiltration into soil, surface runoff, drainage, which is percolation on a large scale, and soil storage of water. So what is a watershed? A watershed is an area of land drained by a single system of streams and bounded by ridges that separate it from adjacent watersheds. We're in the Upper White watershed in Muncie, Indiana. So we have a water balance equation where essentially precipitation is a function of evapotranspiration and soil storage and discharge. So where does land use change this equation? Essentially, discharge is what is influenced by land use. How we manage our land is going to completely change discharge points. So how it's used in an urban setting, how it's used in forests, even no-till versus tilled agriculture land could possibly have a play in this. There's also other influences on the fate of precipitation. Vegetation type makes a huge difference in how water hits the surface of soils and whether or not it goes in or is evaporated back into the atmosphere or runs off into a surface water body. Even two different types of grasses can influence this. Stem flow in trees especially will influence this. Soil management has a huge impact on the fate of precipitation. Whether something is cover cropped or bulldozed is going to change how water is going to be included or released. Soil porosity is highly dependent on surface structure. And so this, of course, will also have a fate on the fate of water. Here you can see some examples of what we've discussed, like vegetation buffer strips on the sides of fields, helping to slow water down, rain gardens being a collection point in urban areas, stem flow example in trees, all of which will influence the fate of precipitation. Here you can see ways that we can manage soil to increase infiltration. One thing to take into account is that porosity helps increase infiltration. So we want to manage our soils in a way that increases pore space. So here you can see some examples of some inventive irrigation in West Texas, and a great example of biotic factors in increasing porosity, which are wormholes. Our earthworms are our friends in terms of increasing porosity. They literally eat soil and poop it out with glue on it to form better structure. I mean, it doesn't get better than that, does it, folks? So as we manage soil to increase infiltration, we want to look at the influence of soil structure and vegetation. In the top left of this figure, you can see where we have a tight, unstable soil structure. So majority of the water that comes onto the surface flows over the surface and only a little will infiltrate. Right below that, in the bottom left figure, a majority of the water will infiltrate an open, stable soil structure where only a small amount will run off on the surface. In the top right, a majority of water will infiltrate into the soil in a tight, unstable soil structure because there's a lot of vegetation on the surface that slows down runoff, forcing the water to hang around and be infiltrated instead. In the bottom right portion of the figure, we can again see a majority of a majority of the water going into the ground infiltrating because of open, stable soil structure combined with surface vegetation that slows it down and decreases runoff. The soil-plant atmosphere continuum is a huge point of resistance. It allows soil water supply to plant roots, where we have the root soil water interface, and we have water evaporation from plant leaves, where we have the leaf cell atmosphere interface. And these are a huge part of the soil plant atmosphere continuum in terms of the water cycle. So for example, when water enters the soil and it's taken up by a tree and then transpired into the atmosphere, it falls as precipitation, where 5 to 30% is intercepted by plants and evaporates back into the atmosphere, whereas 0 to 30% can be lost as runoff. Water can also be absorbed by root hairs in the subsurface, where it can be lost to drainage down into groundwater, or taken via capillary rise back up to plant roots, or back up to the surface where it can evaporate back into the atmosphere again. One thing to point out is how important all of this continual interaction and circular movement of water throughout the plant and soil continuum is to the overall water cycle. So we want to control surface evaporation. Ways that we can do that include putting vegetative mulch on the surface, using paper and plastic mulches on a small scale, for example, in landscaping beds to slow down water from leaving the area. We can leave crop residues and utilize conservation tillage, which is workable on a large scale, to help slow down runoff and increase infiltration to tie into that plant-soil continuum. Vegetative mulches are mostly applied to small areas, like straw on freshly planted grass, for example, and have many benefits. They cut weed growth, they moderate soil temperatures, they increase infiltration and reduce erosion, and they help out earthworms by providing them with food. Here's some examples of wheat stubble left behind to anchor soil, as well as corn growing through last year's wheat stubble in a no-till planting situation. This is ideal, folks. Let's talk about some water quality issues. Preferential flow is when we have large biopores or large pores in general that allow finger flow through macropores directly down into the water table. This is a problem where we have soluble fertilizers, pesticides, and pathogens that can enter the water table. There's also large-scale water movement in soils that are potential causes for concern, especially because this could result in pollution plumes getting into our groundwater. This is especially concerning where we have old abandoned wells, chemical spills, landfills without proper lining, chemicals applied to the surface without professional experience, and poorly drained soils near stream beds. Septic systems are essentially a sewage treatment plant for rural areas that don't have sewage treatment plants. It's an in-ground treatment where water comes from the house out to a septic tank where the solids fall out of solution into the bottom of the tank to be pumped out every few years. And then water goes out to a distribution box, which is taken out to drainage field lines, where the water is allowed to slowly permeate and be treated through the soil, which means that the soil needs to have appropriate drainage capacity. Otherwise, it's going to be a real crappy experience. Ha 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 ha. So here's another look at a septic field. This is why understanding infiltration and percolation matters, especially if you become a professional soil scientist. Here's a real-life picture of a drainage field coming out of a distribution box. And here's one that's not working. Sad panda. Here's an example of a mound system, which is often used in this area because of the poor drainage capacity of the glacial till soils in this region. And here's an example of a drainage field failing and the water coming back to the surface via capillary rise due to poor percolation. So when we test a site for septic system suitability, we auger holes to about 6 feet depth in the area where we have proposed drain lines. And we test the soil's permeability to make sure that it's not going to bring the septic fluids back to the surface. Some more sites for you to check out if this perked your interest. Haha,